Good morning. I am RDK Vitana and my co-host is CS Virvikrama. In this presentation, we are going to discuss about the comparative analysis of exact versus heuristic method in corporate budget optimization. I would like to introduce a core challenge and objective of our project. We are moving to traditional administrative accounting towards a more advanced data-driven approach to decision making. The key challenge we face is how to optimize allocated a fixed budget of 500,000 across the multiple departments in a way that maximize the company's overall revenue. This is not a simple distribution problem. Each department has different needs, different return on investment, and different level of risk. If we allocate too much on one area, we may increase a risk or neglect other critical operations. If we spread resource too thin, we may fail to achieve meaningful impact anywhere. So, our objective is to find a best possible balance. First, we aim to maximize the profit and at the global level, not just an individual department. This means making decisions that benefit the companies as a whole. Second, we must respect minimum operational constraint. Every department requires a baseline level of funding to function effectively, and we cannot go below that. Third, we need to control risk by enforcing maximum limits. While higher investment can lead to higher returns, it also increases exposure. So we must stay with acceptable risk boundaries. Finally, instead of optimizing each department separately, we take holistic approach. We optimize across all departments simultaneously to ensure the most efficient and strategic allocation of resources. This is our dataset and preprocessing. So we get real world financial budgeting dataset in Kaggle, and in that budgeting dataset we have historical funding and revenue records. The core metric is return on investment calculated per department to quantify funding effectively. And the data cleaning part aggregated by department for stability and normalized naming convention. Standardization migrated R&D variant and ensure consistent department categorization. In here, we translate our problem into mathematical model. To make better decision, we represent our budgeting allocation challenge using optimized framework. The goal is maximize the total return guaranteed by all departments. We define this using objective function where we maximize Z to total return that calculated as a sum of each department's return on investment multiplied by amount of budget allocated to that department. In simple terms, we are trying to put more money into area that generate higher returns. However, this optimization must follow several important constraints. First, we have total budget constraint that sum of all allocation must not be exceeded 500,000. This ensure we stay within our available resources. Second, we introduce an operational flow. Each department must receive at least 500,000. That means 1% of total budget, which represent the minimal level of funding required to keep operation running smoothly. Third, we apply a risk ceiling. No department can receive more than 200,000 or 40% of the total budget. That prevent over investment on single area and help manage risk. By combining those objective functions with these constraints, we create balance and realistic model. It allows us to maximize return on return while ensure stability, fairness, and risk control. So let's discuss about the exact method in integer linear programming. ILP is mathematical technique used to find best possible solution when we have a clear objective functions and a set of constraints in our cases. It helps us to determine the optimal way to allocate the budget across the departments. To implement this, we use PULP Python library, which provides a structured and efficient way to define and solve linear programming problems. At the core of this method is the branch and bound algorithm. This algorithm systematically expose all the possible budget allocations instead of checking every single possible blindly. It intelligently eliminates or prunes options that cannot lead the best solution. This makes the search process much more efficient while still guaranteed accuracy. One of the main advantage of ILP is that the guarantees the global optimum. This means the solution we get absolute best possible under the given condition. Additionally, ILP provides the mathematically rigorous results, making it reliable good gold standard for comparison. It is also deterministic, meaning it will always produce the same results for the same input, ensuring consistency. This method is especially suitable for our problem because our objective and constraints are linear and clearly defined. So this is the results that we got. So we allocate the maximum allocation for this RO to get the ROI is 200,000. Thank you. Now I invited my co-host to continue from this here.
Thank you, Raundu. This is the second method, heuristic method. This is the genetic algorithm. We implement the heuristic method using the PyGet library, which mimics the process of natural evolution. Why we select this is robustness to complexity. The real world's financial problems often involves non-convex or nonlinear behaviors. So the genetic algorithms excel in these complex landscapes where traditional math-based solvers may get stuck. And the scalability, this algorithm maintain a steady performance by sampling the search space efficiently and handling soft constraints. The genetic algorithm allows us to use penalty functions instead of a hard no. We can penalize solutions that slightly exceed the budget, allowing the algorithm to explore near feasible regions that might eventually lead to a superior valid solution. The genetic algorithm executed via the PyGet framework. So the achieve a success status because successfully navigating the complex search space to find a feasible budget allocation within the 500,000 limit. The final use budget of for 60,000 and a fitness score of 635 indicate that the algorithm converges on a stable solution. Unlike the exact method, which aggregates aggressively push the highest performing departments to their absolute limits, the genetic algorithm distributed funds more broadly across the organization. This behavior is characteristic of stochastic search processes where the population evolves to a higher ROI areas but maintains diversity to avoid mathematical death penalty of exceeding the total budget cap. For the compare and contrast, we can the exact method behave like a strategic accountant. It identified the departments with the highest ROI and the funneled the maximum allowed amount into them. It only distributed the remaining funds to other departments because the constraint forced it. This resulted in a budget where top performers were maxed out and low performers were minimized. And the genetic algorithm behaved more like an evolutionary explorer because it uses a penalty function for overspending. It was more cautious. It found a solution that avoided the budget ceiling by roughly 40,000. While this resulted in a lower total return, it distributed the budget more evenly across HR, IT, and operations. This spread is a byproduct of the genetic algorithm exploring various gene combinations that satisfy the fitness function without triggering the heavy over budget penalty. So the comparing the two methods, ILP is the deterministic gold standard for linear precision, while genetic algorithm is stochastic and flexible. Genetic algorithm is better for complex nonlinear scenarios in larger data sets. And in the conclusion, the ILP is perfect for this scale, but genetic algorithm offers a scalable alternative. The future work we can includes the exploring hybrid method, genetic algorithm plus ILP approaches, and incorporating diminishing returns. And thank you.